Up next is Steven Kontra, a dual master's student in civil engineering and wood science. His presentation is Earthquakes and Tall Timber Buildings, Testing Full-Scale Designs. Welcome, Steven.
Thank you, Eric, for the introduction. Hi, everyone. I'm Steven. This is what I do. So you may be wondering, do you guys give dance lessons to buildings in civil engineering? Well, not exactly, but you're not too far off. We put buildings through earthquakes over and over and over again to test their performance. What you're seeing here is a full-scale, 68-foot-tall, 6-story building that's composed of timber products specifically engineered for large-scale applications that we call mass timber. This mass timber building is sitting atop the world's largest outdoor earthquake simulator, or shake table. This shake table can simulate any earthquake in recorded history. Just imagine you were a giant and you could pick up a 68-foot building and place it in a massive earthquake anywhere in the world in any point in recorded history. That's what we can do with this. What you saw in the video was a simulation of the infamous 1994 Northridge earthquake. This earthquake took 57 lives and caused $60 billion in damages and economic loss. So how do we make sure history does not repeat itself? How can we prepare our communities to face such a risk? Well, the most efficient way we can prepare is to design our buildings to be resilient. Resilience is a critical concept in structural engineering, and it refers to how quickly a building can bounce back after a natural disaster. We measure this on a spectrum, where a building that can be fully operational right after an earthquake, that's resilient. A building we need to demolish, not so much. Now, when we talk about resilience in the past century, for tall buildings, we're primarily talking about the use of two materials, concrete and steel. In fact, as it stands today, 99% of non-residential construction use concrete and steel as their primary structural material. That's a big problem for our planet, because just the production of these two materials alone account for 12% of global greenhouse gas emissions. To put that in perspective, if concrete and steel formed one country, they would be the number 3 emitter of greenhouse gases worldwide, only behind, guess who? The United States and China. For this reason, researchers all over the world are looking for ways to make our buildings more sustainable. And mass timber is a very promising alternative. These products are strong, they're versatile, but best of all, they can be produced at a fraction of the carbon footprint. Let's think about how we get timber products in the first place. They're from trees. Trees take in carbon dioxide from the atmosphere, and they store that carbon within their very wood fiber. And that carbon can be retained in wood products and can be stored in buildings. Essentially, we're turning our buildings into carbon storage devices. Now, mass timber is still relatively novel, so you may be wondering, what does it look like when we put mass timber in large buildings? I'm not sure if you realized, but mass timber designs have been embraced widely, even here in Oregon, and even right here on this very campus. Anyone walk through the College of Forestry lately? Or perhaps you've heard of the new Collaborative Innovation Complex coming in 2025. That'll be mass timber too. And oh yeah, Anyone flying into Portland starting this summer will be greeted by one of the grandest displays of mass timber construction anywhere in the world. Let's get back to our building. In our building, we're testing a new mass timber technology that's resilient and scalable for tall buildings. We call it a mass timber rocking wall. We also sometimes refer to it as a structural spine. Why? Because the rocking wall serves a similar purpose for the building as the spine does for our bodies. When the earthquake shakes the building, the spine makes sure that all the buildings, all the floors are moving together, so it's one building, and also has a self-centering capability such that after the shaking, the building can come back into alignment. Now, we don't just shake these buildings for the joy of watching them dance. We implement a specific test program to learn everything we can about mass timber designs and how mass timber buildings behave in earthquakes. We fitted our building with 700 sensors to measure things like how fast the floors are accelerating, how components are moving relative to each other, and how the building is moving and drifting in the earthquake. And once we had our sensors installed, we subjected our building to 244 earthquakes sourced from all over the world, of all different types and of all levels of magnitude. And you might expect a building to go through so many earthquakes to be in pretty rough shape, right? Well, that's not the case. We saw no structural damage at any phase of shaking. What does this mean for us? It means we can design mass timber buildings to the highest level of resiliency. From our tests, we collected a tremendous amount of data that we can use to validate our design approaches. And we can share this validated design approach with the engineering community that lets them perform their own resilient designs using sustainable mass timber material. My friends, our building sector is ready for something new that's resilient and sustainable. I say, it's time we shake things up. Thank you.